Hope you all enjoyed lunch. My pleasure to open this afternoon session with a talk from Tor Fjelde from the Turing.jl group, I guess, here in Cambridge. So Tor, over to you. Thank you very much for coming.
Hello, thank you for having me. Unfortunately, I couldn't make it in person. I'm currently in a small town in Germany visiting my my partner's family. But hopefully it will be okay over Zoom too. So yeah, as I said, I'm working on this probabilistic programming language called Turing.jl. I'm a PhD student on the Hong in Cambridge. And this has been like something I've been working on now for the past 4 years, I think, as part of my PhD, I suppose. So that's what I'm going to tell you a bit about today. So maybe I should just get started. All right. So, yep, as said, my name is Tor Fjelde, work on Turing.jl. I'm currently associated with both the Alan Turing Institute and the University of Cambridge. I'm going to put on a timer so I have roughly some sense of how much time I spent. And I'm going to tell you a bit about Turing.jl. And usually when I talk about this, I start with telling people a bit about Bayesian inference and sort of what that is all about. Unfortunately, I haven't been able to attend the previous seminars, but I'm assuming that Bayesian inference is already fairly familiar to the audience. So usually what I say is that, we have some real world data, curly D. We want to determine parameters theta given this real world data, curly D, i.e. want to inspect the posterior. Can I get like a laser? Perfect. Posterior of theta given the data. Bayes' rule tells us that we can decompose this into a likelihood term and a prior term. And then we sort of typically write this down as a generative model, where we sort of sample the theta from the prior, and then we sample the data from the likelihood. And then in Bayesian inference, we then condition this data on some real world data we have access to, and then we try to infer the theta. As I often show this sort of simple bias cone example with this sort of nice animation of the posterior converging. And then I tell people that this is generally not what it looks like in practice, because we often run MCMC and then it doesn't look as nice as this. Basically, you don't get you can't just update as a new observation comes in unless you're using specific methods, right? Another example, of course, is like a standard linear regression where you now have tuples of x, the input location is x and the sort of output location is y. And here we have some intercept gamma, we have some slope beta, and then we just sort of have this sort of simple Gaussian noise on the observations. And again, we can sort of, do inference for a bunch of these realizations and have something that we see like the posterior converges nicely to something that resembles the true parameters, for example. And so overall, Bayesian inference is is a thing that we want to do, but generally it's somewhat difficult to do in practice. This generally comes down to the fact that the posterior is often not available in closed form, and particularly not for interesting models that we often end up looking at. And so it requires various sort of approximate methods to actually inspect this posterior theta given data. Typically, at least common families to use is then Markov-Chain Monte Carlo, variational inference, and so on and so on. And these can be both annoying and difficult to implement. It requires, implementing them well requires software engineering skills, but it also requires sort of statistical knowledge about these methods. Even like testing them, making sure that you actually done everything correctly is very difficult due to the fact that they're so stochastic in nature, and so they can do something reasonable on examples that you give it, but then even though you sort of have a bug in your implementation. And so this is kind of the summary of Bayesian inference, I suppose, like a principal way of incorporating prior knowledge into the prior. It allows for quantification of uncertainty, ignoring sort of model misspecification, all these things, but is non-trivial to do for interesting problems, and it requires sort of both computational resources and a sort of knowledge of the inference methods to actually do these things. So this is kind of where, in my view, probabilistic programming comes into play. So I view probabilistic programming as effectively like a way of democratizing Bayesian inference, right? So it's all about making Bayesian inference approachable to a wider audience. And so the user, as what we're kind of hoping, is that the user should be able to write down their model, and then the rest should be fairly sort of automatic, right? Because often the people that actually have interesting sort of domain-specific problems that they want to do inference for, they have parameters they're interested in for a simulator and so on, aren't necessarily the people with the statistical knowledge and the software engineering skills to actually go and do this, right? So often we see people working, for example, R, using stan, and then it's quite like a simple thing to do. So that is kind of I think the aim of PPLs in general. And so I view as probabilistic programming languages as like a suite of tools that allows you to easily specify models, but also provides a suite of inference methods that you can then apply to different models. Preferably as much of this is kind of, automatic, as like simple as possible for the user, so that people with domain knowledge in, say, epidemiology or biology, they can come with their problem with their data and they can perform Bayesian inference for their problem. And to do this, there is a lot of different approaches. So I was curious, has there been any talks about any other PPLs before this? So like, roughly like where?
Yeah, a couple of talks, yeah.
Perfect. Any particular PPLs?
Nothing specific, more
broad strokes, basically.
Sort of broad concepts, really, yeah.
Gotcha. Okay. Yeah, so I'm not going to go through all of these in detail, but there's like tons and different approaches, right? And Turing is one of them, but there are many different approaches. They all have this sort of pros and cons, right? I'm just going to kind of skip to the parts where we're looking at these different ones. And so these ones, I'm just showing a small subset. These are like some of the fairly popular ones. And I can kind of group them into like certain categories. So I'd say like stan and bug. So stan is, been used extensively in the scientific computational literature. It's been around for a few decades now, I think, and it's been incredibly successful, incredibly useful for people in different disciplines. And then bugs is kind of this, it's been around for ages. It's one of the first PPLs, and it's kind of, one of the foundations effectively of probabilistic programming. And then we have these Bean Machine, PyMC3, and Pyro, which are in Python, and they use sort of these underlying graph computational frameworks that have been popularized in machine learning. Now we have some other ones like Anglican. And so the way I view this is that these stan and bugs, they kind of have this custom DSL. So the way you specify the method, is they specify the model. It happens in one language that they sort of tell you the syntax of. And then the actual implementation is a low-level language like, say, C++ in Stan's case. And then they provide simpler interfaces for higher languages like Python, R, and Julia. And so this is kind of where the users interact with the language, but all of it is run in a different language, say, for example, C++. And then there's these red ones, which is in Python. As I said, relies on these machine learning frameworks. And that means that they're very, very fast and are particularly good at models that involves a lot of sort of linear algebra operations. But it does mean that you generally work with a host, like a subset of the host language, which is Python in this case. And so you kind of have to be a bit careful. You can't just implement things naively. And for people that have sort of extensive machine learning experience or like software engineering skills, this is like works really well. But then if you don't have this, it can be quite intimidating and a bit difficult to work with. And then there's sort of like Anglican, which is everything happens in the same language. So this is also similar to Turing, as I'll show you. And that means that it's very flexible because you can sort of customize it, because the implementation of the model, the implementation of the inference algorithms, they're all in the same language. But in Anglican's case, for example, it hasn't really been used that much for in scientific disciplines, just because I wouldn't call it Clojure, which is where it's implemented like esoteric language, but it's less commonly used for scientific applications, I would say. And so that gives us to Turing.jl. And so it's very fair at this point, obviously, like to ask if this is the perfect PPL, and it's far from it, but it's like kind of different in the approaches taken from the other ones. One of the big ones, which I'll talk briefly about, because I assume it's not something that's like super well known, I would suppose, is the Julia programming language, which is what Turing.jl is implemented in. So here I'm giving you an excerpt of what the original, like why we created Julia, a blog post from 2012. It is, I'm not going to quote this entire thing, but they sort of want like the speed of C, the dynamicism of Ruby, familiar mathematical notation like MATLAB, general programming as Python, easy statistics as R, and they want it to be interactive and they want it to be compiled. So they sort of, they want everything basically in one language. And then the question is, did they succeed? Sort of. They did a pretty good job. So it's quite simple to learn. It was very, very simple to learn, and it's very familiar to people with experience in like sort of high-level programming languages. And it's very, very fast. But once you get to like some of the ickier parts, it's, you kind of need to know what you're doing. But you can always make it faster, which is a very, very nice thing. So overall, it's pretty good. I'll show you a brief example here. So This is an example where we're estimating sort of pi by just doing Monte Carlo sampling in this unit cube, and then we count the number of times the sample ends up inside the circle, and then we basically take that, use the ratio, and compute the ratio with how many number of points we actually sampled. Then we multiply by 4 because that gives us the area of the circle, right? Sorry, that's to give us actually get us pi from the area of the circle. And so here you see the Python implementation. It takes 390 milliseconds to run when I do 1 million Monte Carlo samples. And if I'm going to do this in Julia to show you the comparison, so in Julia, we have this very nice thing called irrational numbers, and that's a built-in proper type. And so I can just take that type and then convert it to float 64, and I'm done. Yeah, obviously, this is very much cheating. So I could also just implement the method in Julia itself. And so here you can see it looks very similar. We have this function, estimate pi. Again, you have this num inside, num within, just differently named. Do a for loop over the number of Monte Carlo samples we want to draw. We sample them, and then we just count the ones that fall inside the circle, and then we compute as the same before. So these are like basically one-to-one mapping effectively. But the runtime is very, very different. So here you can see the Python one takes 390 milliseconds. The Julia one takes 3.4 milliseconds. So this is 100-time sort of speed up, and we haven't done anything. And so Julia does this thing where basically Python interprets each of these lines, and so it's going to be quite slow. What Julia will, when you define this method, it will register this method as being existing. And then when you call it, say with an integer, it will actually specialize this. So it will sort of go in here and it will say, this num total now is an integer. This is an integer. This is an integer. These are floats, and so on and so on. And it will compile it down to machine code. And so that means the first time you call this, there's a slight delay. And then afterwards, it's very, very fast because it caches that computation. Not the computation, but the compilation. And so this is kind of the entire premise of Julia, is that you can write whatever you want in here, right? So just because you could, for example, vectorize this implementation on the right in Python, and it'll be much, much faster. But kind of the idea is that you can write this naive code and it will generally be quite fast. And then you can also vectorize and optimize, and you can squeeze out more performance if you want to. So here is like this plot from the Julia website where they show a bunch of micro benchmarks, and you see C here is the baseline. So this is the line here. And then you see Julia, which falls all the way on the left here, which generally, being one of the fastest languages. And this is comparing to, the likes of like, let's see here. So you have C here, Lua, JIT, and Rust, and so on and so on. So as you can see, it's a fairly fast language. I'm not going to go into this, but you can basically look at whatever parts of the entire compilation pipeline you want. So you can look at the machine code if you really, really want to, for example. But, And then finally gets me to Turing.jl, which is implemented in Julia. So what is Turing? It is a general purpose probabilistic programming language, meaning that it's sort of meant to be quite general in what you can do with the kind of models you can define in it. It's fully implemented in the Julia programming language, which means that everything is Julia, and so you can mess around with it. You can sort of implement your own distributions in Julia. You don't have to drop to some other language, and so on and so on. It also has this syntax that's very similar to, because it's in Julia, it's very similar to like MATLAB, Python, and R. So there's a lot of people that use PPLs that are familiar with these, come from this kind of side of things. And it's been like growing in popularity. And in particular, I would say over the past 3 years, we've seen quite an increase in like publications that are citing the Turing paper, and people sort of being engaged in a community and so on and so on. And on the right here, this is what a Turing model looks like. So as you can see, we do using Turing to import a package. This is just standard Julia code. And then we define this model called demo, which is a standard Julia function with this sort of nice tilde syntax. And so here we have this theta, and we're sampling this from like a prior when we write this generative model. And then we have this curly D here, and then we have this sampled from a likelihood, which takes in the theta parameter that defines the likelihood. Then once you have this thing here, then you can instantiate the model. So I'm just calling the demo, and then I get back a model instance. And to condition the model, because right now, this is just a generative model with 2 variables, right? So it defines this joint distribution. And then I can condition it on the curly D, this variable, being equal to some data I have access to. And now I get back a new model, which is the model with the conditioned data. And then I can finally sample from the posterior using, say, the no U-turn sampler in this case. Is there any questions about this? Does this seem sort of fairly understandable. You see how this relate back to the notation basically we saw earlier, right? So here we have, on the right here, we have the mathematical notation for like the linear regression example. And on the left here, we have this sort of Julia implementation of it. So any questions about this? So is this like, that seems to make sense?
I have a question.
Cool.
One question.
Yep.
Sorry, I have a question about scoping, because it looks like the variable you define in the function are accessible outside the function.
Well, so this is more like, this is kind of constructing a dictionary or like a name tuple of sorts. I'm assigning it this thing. So this is like fed into the model later. So this is more like, think of this as like a dictionary basically that I'm passing into the model. So I'm not defining this variable. It's more like I'm telling the model that now the thing that corresponds to this inside your model is going to be fixed to this. Does that make sense? Yeah. One thing that you kind of want, if you want for the PPL, it kind of, I said, like the entire point is opposed to sort of democratized Bayesian inference. And so then it's important that these typical workflows that you have in a PPL when you're doing Bayesian inference is easy to perform, right? So I'm pointing to this paper here, which is just a great resource on this, and I very much recommend it if you haven't come across it before. But what it consists of is typically this kind of thing. So you sort of define a model in mathematics. So highlighting this here, and what that looks like in so the mathematical notation is this. This is like a log linear model in this case. Then the next thing is you define a model in the PPL, Turing.jl in this case. And this is the highlighted block here. You can see what it looks like, right? So it's fairly simple, just similar notation as we saw before. Very much closely matches the mathematical notation, which can be quite nice. Then we perform these prior checks, where the idea here is to sample from the prior and sample data from the prior on fixing some parameters and to make sure we can actually identify the true parameters. So here what I'm doing is I'm taking in a model, which is a joint model over all the parameters, including the observations, and I fix some particular parameters. And then I sample from the model and I sample the Y variables, which is what we're going to have as observations. And then from that, I sort of run inference on this model conditioned with these new Y values. And then I make sure that, okay, the actual under this prior, I can actually recover the true parameters. This is like a very common thing to do that's like incredibly useful, just to make sure that the inference algorithm that you're using works with the model that you have in front of you. And then finally, you can perform inference, conditioning, and then you sample. And then once you're done with sampling, you sort of get a bunch of summary statistics. We have like, effective sample size, R hat, all these typical values. And then you can easily perform prediction or look at like, so here's the predicting and here's looking at the actual posterior that you generated. And then, if model was good enough, then you're kind of done. If it wasn't, then you rinse and repeat effectively. So all in all, this is kind of what I would say the benefit of Turing is, that it's very convenient and has good performance, similar to design philosophy as Julia, which is accept everything and optimize when possible. And then in models are Julia functions, distributions are Julia functions, and everything is kind of in Julia, which means that it's very, very easy to introduce new things like new distributions, new samplers, and these kind of things. It's very, very trivial because you don't have to drop to say C++ to do it. You can still stay in the language that you're modeling in. Currently, I say currently because this is not something that's impossible. It's just that we haven't done it yet. Like we don't do, for example, automatic marginalization because we make very few assumptions about the model, but this is like technically possible to achieve. We just haven't done it. And naive implementation of a model might not be the most performant one. So you might still have to sort of tweak the performance, but still when you're tweaking it, you're still in Julia, which is quite nice. And so you don't have to sort of drop down to another host language, for example. Here's just like some example of people using it in practice. So it's not just sort of us using it. I'm going to skip this and then finally get to a quick example of an SIR model in Turing.jl, which demonstrates nicely this kind of everything is Julia. And so it makes it very easy to extend it in some sense. So an SIR model, for those not familiar, is sort of a susceptible, infected, recovered model. And the model is a spread of an infectious disease, where this beta parameter, which is one parameter of interest, is the transmission rate. And then there's a gamma, which is the recovery rate. And then we have sort of a data is the number of infected, denoted by I. And we want to determine the beta and gamma, and the fact how this sort of evolved through time is described by this differential equations there, where the susceptible sort of decrease as more people get infected, then the infected is increased by the infected amount, and then decreased by the people who recover, and then you end up in a recovered state, and then you're sort of immune basically. So hopefully, if you live through COVID, like most of us have, then this is probably something you've seen before. And so in particular, I'm going to look at this very, very simple example of an outbreak of influenza A at a British boarding school from 1978. It's a very classical one. The 763 male students, 512 became ill during the 14-day outbreak. At day 1, only a single student was infected, i.e. sort of the I at times 0 is equal to 1. And then we have sort of 14 days of observations, and we want to infer the beta and the gamma. So what I'm going to do now, I'm going to do something that people generally shouldn't be doing, which is do a bit of live coding. I'm not going to do much, and I'll be very, very quick about it. So this is just showing, is this, like, can you see the text there? Is it large enough, or should I make it larger?
No, it's good.
It's okay.
Good. So here I'm just loading some packages. So I'm running this code in this Julia REPL here. So this is similar to like a Python REPL or Python that you might interact with. This is just, and then this is just a way of like downloading the data. So nothing to worry about. We have sort of data frames that I load from the CSV file. So I'll just do this, and we can see it here. Now it's, because I have such a small terminal, you can't really see it. So let me just show you something maybe. No, sorry, first data. Let me show you data. Maybe this works. Yeah. So it's just like the REPL is so small that you can't really see it. And so we have like data in bed. We have the dates of it. Maybe I should show you the columns. We have column 1. Okay, let me print the entire thing. There we go. So then we can see we have the date, we have the embed, and we have convalescent, which we're not going to worry about. And so really just what we care about is this variable here, which is number of people in bed, which is considered to be a proxy for number of people infected. Now, the nice thing here is that what I'm going to do, I'm going to load this package called differential equations. So this is a Julia package that does solving of differential equations, and it does it very, very well. Then I define this differential equation system. So here you can sort of see it's very similar to the mathematics we wrote down. It's worth pointing out that us, the Turing.jl people, have nothing to do with this differential equation package. Right? So this is not something we have anything to do. We just use it quite extensively for applications. Then I'm setting up the problem, solve it. So this is just setting up a problem here, OD problem, then I solve it. And then I'm going to use this stats plus package. Again, not something that we in the Turing.jl sort of organization work on. We just use it. And then I can plot it. And then you can see here on the right, you can sort of see example path for some particular parameter I picked. And then you see the black dots is the data. So now what I'm going to do is I'm going to take a Turing model. I'm going to define this negative binomial too, because I want this. And I'm going to define a Turing model like here. So I'm defining a SIR model. I'm giving it prior on the transmission rate, the recovery rate, dispersion parameter, which is an input to the likelihood. Then I take this ODE problem that I defined before, that I just solved, right? I'm going to take this and I'm going to remake it inside the model with the new parameters, right? Because these parameters are going to be sampled at each of these tilde statements. And then I solve it. And if it's a success, then we just continue. But if it is not a success, we just add minus infinity to make sure that we reject this sample because of numerical errors or whatever. And then we get down here. I extract the infected state. So this is the state that was I. And then I simply iterate over the observations in bed and use this likelihood here. And then I can, and that's sort of the accumulation of the likelihood. And so what I can do, I can run this. So now I instantiate the model as we saw before. I had this SIR model. I call it unprob. Now I condition it on some data. And now I'm going to run sample, no U-turn sampler, and it takes 1,000 samples. And I'm doing 4 chains. And I'm using MCMC threads there, which just indicates I'm going to do it in a threaded way. So I'm going to do it in parallel, right? So what you see, I'm sampling with 4 threads. It did some initial step size thing solving. And then, unfortunately, you can't see the parameters here because of the REPL. But then what I'm going to do is I can, so you saw that one thing is that it's finished in like, a second, basically. And this ran 4 chains in parallel for like 1,000 iterations plus adaptation. We're also differentiating through this entire model because no U-turn sampler requires gradient information. And all of this is happening kind of like automatically. And this is kind of a very, very nice example of where we have differential equations. We just put it into a Turing model and it just works. If you wanted to, you could solve linear programs inside the model. You could do kind of whatever you want. So we basically let the user kind of, we give them a shotgun, and if they want to point it at their foot, that is allowed. You can do that if you want to. Don't recommend it, but it's possible. And so what I'm going to do, I'm going to extract some of the parameters of interest of the chain, and then I can, for example, visualize them, for example. So here you can see the trace plots for the different parameters and the densities and so on. I think in the interest of time, I'm going to stop here, but yeah, this is kind of the, so lots of things you can do now once you got into this point, basically. Finally, I'll just point out that this is collaboration sort of done with multiple people. So here you see some of them, and here you see even more of them. And it also wouldn't be possible without the Julia ecosystem as a whole, and many other people that contributed to Turing.jl. But yeah, thank you for listening. So if there's any questions, I think that's a good time to take them.
Thanks very much. So time for a couple of questions. One at the back, Carl.
Hi, so thanks for the talk. Has anyone tried to combine Turing with something like unitful to demonstrate that you're able to get some of those units preserving and units checking outcomes, like take advantage of that?
So for those not familiar, like unitful is a package where basically it allows you to lets you do stuff like, say, I can write down I can say like, 1 and then do this, for example, which is like 1 millisecond, for example. And so this can be nice in particular physical systems where you want to sort of make sure that you do like this dimension checking effectively, where you're checking that the units all make sense. And so I know for a fact that people have done this in Turing. I haven't used this myself, but I know it's definitely possible. And so people have actually used this as an example. So there's nothing stopping me from, for example, I could easily just take these infected for observed here. And if I wanted to, I could, add like a unit to them. I'm a bit uncertain exactly how it goes, but like I could, there's nothing stopping me from doing like, a person, for example, something like this, right? I could, for example, do this and then like do something like this, and that would. So now I was basically say that, actually now this thing is going to be observed. These observed ones are actually going to be in the unit of one person, and everything should still just work. So that is like, so that just shouldn't really be a problem.
Yeah, and then sort of more critically, if you have gone awry in your specification,
like unitful would then let you say, oops, you tried to multiply people by tens of people or something like that, and now
exactly.
Yeah. Okay. All right.
There's one like caveat, which is like, I think at like all the innermost computation, we do expect sort of floats or arrays or something like this at the moment. So that might be like, you might run into like a bug where maybe if you try to make something here unit for like the beta unit full when it hits this or something like this, but that's like, I think that's very, very easy to fix, and that would be like an exception rather than the rule, I would say.
Good, thanks. Aaron.
Yeah, thanks for the really nice talk. I particularly appreciate it because it's helpful to me to get an appreciation of these different approaches to solving the same problems. So I wanted to ask you if you could give us a little bit of a status update with respect to two aspects that are common in all of these problems and how Julia is doing. So in particular, automatic differentiation, like how does that stand with respect to what Python is doing and so on, and then the use of GPUs?
Yeah. So I would say like both. So it depends. Like, so when it comes to automatic differentiation, there are multiple different approaches to it in Julia, and this is like a thing that we kind of get for free in Turing because other people are working on it. But it does mean that most of them are trying to differentiate like the host language. There's also, I'm pretty certain in the audience, I think I saw Will Tabot, which is working on one of these approaches. So he can probably give you even more information afterwards. But I would say like the state of the art now is that things are going, it's much better than it was a few years ago. But it's still like, if you write a model in a way that's compatible with JAX, for example, right? JAX will be faster unless you kind of, like I would say as in general, like if you write it in the subset of Python that is compatible with JAX, you would generally get a better performance out of that. And similarly for GPU, you would get better GPU utilization. Turing.jl doesn't currently support GPU. There's nothing technically stopping us, like we could do it. It's just a matter of like man hours effectively.
Is that active area of development in the community?
Yeah, for sure. I mean, AD is a huge, like definitely very active. And also GPU is also very active. GPU support is very good in Julia as a whole. Like it's very easy to use. you literally just do like CU, and then if you have like ones here, and then this is now the GPU basically, and then it works like normal. It's just that you need to avoid like scalar indexing and stuff like this, and this was just something we need to work on in Turing.jl specifically. But the rest of the community, like differential equation, I think is like very good for GPUs and stuff like this.
Thanks. Okay, so in the interest of time, I think we'll move on, but let's just thank Tor again.
Thank you.